Hello, my name is Kenneth Flores, and today we'll be doing experiment 15, which is basically establishing an equilibrium constant for methyl red solution in water. So like we've seen before, we're using Beer's law to track concentration changes. So this is, of course, the absorption is equal to epsilon, the molar absorptivity coefficient, multiplied by the path length, and finally multiplied by concentration. So when you place methyl red in solution, you're going to have it react with a water molecule, which then will create a deprotonated form of methyl red, as well as a hydronium ion. So if you have this in solution under a pH of 4.4, you're going to have predominantly the protonated form of methyl red. Anything above a pH of 6.2 will be predominantly the deprotonated form, and in between those two ranges, you're going to have a mixture of both. So the protonated form of methyl red will strongly absorb at 525 nanometers, where the deprotonated form will absorb at 430 nanometers. Now there will be an overlap with those two solutions, so that's something we're going to see in the concentration calculations later, where we can kind of correct for that overlap in absorption. So for today's experiment, we're going to be following the normal PPE protocol, which include goggles, gloves. We want to ensure that we have a lab coat all the way buttoned up, as well as closed-toed shoes and long pants to ensure that we're not showing any skin around the ankles. For anyone with long hair, we want to make sure that we tie that back to make sure that's not getting into any of the chemicals.
Hi guys, I'm Carolina and I'm going to guide you through the experimental portion. We're going to gather all our chemicals. These are going to be our starting materials. We have methyl red, hydrochloric acid, acetic acid, and sodium acetate. If you look carefully at the labels, they each have their respective concentrations. Now to look for how to make these solutions, refer to your lab manual where you have the list of the recipes per solution. We're gonna have our 100 milliliter volumetric flasks where we're gonna put our solutions in there, and then at the very end, we're gonna dilute it with deionized water to the mark, which is about right here. And I'm gonna go ahead and prepare the solution so you guys can see what they look like. So I've gone ahead and prepared the solutions for you all. My suggestion is to place a white piece of paper under your solution so you can see the different colors of the vials and have a better contrast. And essentially here we have the acidic solution, solution 1, solution 2, and the basic solution where we see a gradual change in color until we get to the yellow. Now to begin our spectrophotometer measurements, we're going to get our solutions from our volumetric flasks and we're going to go ahead and pipette them into vials. Now I have one pipette per solution and we're going to ensure that we don't mix any of the pipettes into the other solutions, that way we don't cross-contaminate. I'm going to start with the acidic solution and we're going to pour it into the vial using the pipette. So this is what the vial should look like. Once we're done pouring the solutions into the vials, we're going to have to pour our solutions 1 and 2 into beakers, and that will allow us to make the pH measurements. And you want to pour enough of the solution into the beaker that will allow the electrode of the pH meter to be fully submerged in the solution. In order to get started with the spectrophotometer analysis, we're going to need a few materials. We're going to need a squirt bottle of DI water, a waste container, and a pH electrode, which we'll plug into the spectrophotometer along with the solutions that we'll be measuring. We're going to go ahead and begin with the absorbance and transmittance measurements for each of the solutions. And to begin, we're going to open up the spectrophotometer software. I do want to point out that you can select the wavelengths of interest, and for this experiment we have 430 and 525 nanometer wavelengths. Once you open the spectrophotometer software, you're going to select to measure absorbance. and you can select the wavelengths of interest that you want to look at. In this case, we want to look at 525 nanometers and 430 nanometers. As is the case when we begin measurements, we're going to insert our blank to calibrate the instrument. Now, I'm going to continue by placing our vials of the different solutions into the spectrophotometer and measure their absorbance and transmittance. So after we measure the absorbance for the first vial, we're going to repeat the same process for the rest of the vials. So now we're going to measure the pH, and we're going to grab our pH electrodes and plug it into the microlab. Okay, so after we plug in the pH electrode, we need to make sure that we input it into the software and add it as a sensor. As we're adding the pH electrode as a sensor, we're going to make sure that we use the factory calibration that is already input in the system. Once the pH electrode has been added as a sensor, the pH will be displayed at the bottom right corner. As I previously mentioned, the electrodes have to be handled with care, and this is specifically because they're always in an electrode solution when they're not being used. And so what I'm going to do is I'm going to remove it out of the solution and clean it with DI water so I can then use it in my unknown solutions. Now, as I'm rinsing the electrode with DI water, I'm going to make sure that the DI water is being put into a waste container. Now, we're ready to put the electrode into our unknown solution. We're going to wait for the pH on the monitor to stabilize, and once it's stable, we can record that as our pH measurement. To ensure that your solutions were prepared correctly, you'll know because the pH will fall between 4.4 and 6.2. So, in order to put our electrode away, we need to do the same thing, clean it off with deionized water, and put it back into our electrode solution. So the important thing here for the spectrophotometer is to get the absorbance and transmittance of all our solutions and the pH of just our solutions 1 and 2. And that will be used to be able to do the calculation portion.
So for the calculations today, the first equation, or equation 5, which you guys can find in your lab notebook, really doesn't need any manipulation. The only thing this is showing is that absorption values are coming from both identities, the protonated and deprotonated form. So if you look at equations 6 and 7, these are for calculations of either the protonated form, which is equation 6, or the deprotonated form of methyl red, which is equation 7. The MR in brackets is referring to the dilute concentration of methyl red for that solution. Now, there's important things that you need to look at and pay attention to make sure that you're plugging in the correct numbers in the correct areas. So if you look at A, this is referring to the absorption value, but which absorption value exactly? If you have a subscript of B, this is referring to the absorption value of the base standard at the respective wavelength. So for this first one, we're talking about the absorption value for the base at 525. Right next to here, we're talking about the absorption value of the solution at 430 nanometers. Of course, you want to make sure that you're staying consistent. Whenever you're looking at a solution, use those values for that specific solution. So you want to make sure that solution 1 is used for both formulas, and now when you're calculating for the solution 2, you use those values for those two specific formulas. So once you're able to calculate the concentrations of the protonated and deprotonated form, what we're going to have to do is come up with our K's of A expression. So as we've said before, in the K's of A expression, this is going to be products over reactants. So the products for this reaction would be the hydronium ion concentration, as well as the deprotonated form of the methyl red. That is in the numerator. In the denominator, we're taking the concentration of the protonated form of the methyl red. Now, to calculate for the hydronium ion concentration, we can do this simple manipulation where the concentration of hydronium ion is equal to 10 raised to the negative pH. So that's the reason why we took the pH of each solution. Now, once we're able to solve for the hydronium ion concentration and solve for the K's of A expression, the last step is solving for the pK's of A. Now, this is a very simple equation. The only thing we have to do is apply negative log to that K's of A value, and that finally gives you your pKa. So once we're able to solve for the pKa, the last thing you guys need to do is solve for the percent error. So to calculate percent error, we're just going to do the actual minus the accepted value over that accepted value. Now make sure this is the absolute value multiplied by 100 so that you end up in a percentage. So for the percent error, the closer you are to 0, the more accurate your results are. Now we're not expecting anything 0 exactly, but the closer you are to that value, normally the better your results will be.